Welcome back to the sixth video about capacitive liquid level sensing. In the previous video, we tried to measure the capacitance of our little sensor here using just an Arduino Nano Every with one external resistor as an additional part. And while that worked in principle, we were restricting ourselves, of course, to the mechanisms available in the standard Arduino environment. The accuracy of our measurements was lacking, and we discussed the reasons for that in that previous video. Card here, link in the description. This time, still just using functionality available in the standard Arduino environment and still using just a single external resistor, we will do hopefully better. Enjoy! So, what problems did we face last time and how can we avoid them? Basically, we built two types of software-based oscillators. The first type relied on the Schmidt trigger input stage of the input pins on our ATmega 4809. And that was not very accurate in creating a stable frequency. And after the fact, we realized that these Schmidt trigger input stages are lacking. That said, an ATmega 4809 also has an analog comparator built in, but that's not directly accessible in the Arduino environment. But if you don't shy away from a little bit of bit banging and register writing, then maybe you could improve that method. But we want to stay within the Arduino environment for now. For our second software oscillator, we utilized an analog to digital converter. And it turned out that the sampling frequency we can achieve of about 10 kilohertz was simply too low to switch from charging to discharging and vice versa in a timely fashion to get an accurate frequency from the capacitance of our sensor. But still, we can measure, or we can assume that we can measure a 1 voltage at one point in time with a reasonable accuracy. Now, in part 4, card here, link in the description, we were perfectly capable to measure with reasonable accuracy the frequency of an external RC oscillator based on a 74HCT14. So we can count and we can do timing quite good with our little microcontroller here. And so we come full circle to part 2 of this series, card here, link in the description, where I showed you, the math describing the charge curve of an RC element. I didn't do that for fun or just to show off that I know that formula. You find that in every textbook and even on Wikipedia in the correct form. Anyway, we can rearrange that formula into this form, and then if you can measure all parameters at one point of the charge curve of our RC element, you can from that calculate the capacitance. And all we need to do is to have an exact timing when we are measuring and a reasonably exact voltage measurement at that point in time. And that's exactly what we will do in this video. Remember, these little multifunction testers work exactly on that principle when measuring capacity. 2 links in the description if you want to have a look into the code of these things, which is quite convoluted but really optimized for that purpose. Before we have a look at my code, which is really more optimized for ease of reading than for absolute measurement accuracy, a short reminder about our hardware setup. So nothing changed. We still have at pin 20 of our nanoEvery resistor here, which is used to charge and discharge our sensor, which is really just a capacitor with variable capacitance. And through pin 21, we can measure the voltage across our capacitor. And pin 21, incidentally, at least for a nanoEvery, is also an analog input which can be connected to an ADC. Oh, and I almost forgot. The resistor value I did change down from 10 mega ohms in our previous videos to 5.1 mega ohms. The reason for that I might explain later because it's just a detail. So here's the code. We have much more constants now. So we have, of course, our constant bytes here for my sense pin 21 and my drive pin 20. That's unchanged. Then we have now a constant unsigned long, which is the charge time, how long we will charge our capacitor in microseconds. 250. That's experimental, okay? You can, if you know about the capacitance of your sensor, you can measure it with a multitester or your multimeter. You can guesstimate what a good value is, because after tau, you remember tau is capacity times resistance. After 1 tau, you are at about 63% of the charge voltage, and after 5 tau, you are nearing 100% of your charge voltage. And the goal here was with the charging to stay within, let's say, 20% of 5 volts, so full scale value of my ADC, and below 90% to give a little bit of a buffer and not run into overflows. Then we have unsigned long, the discharge time in milliseconds. That's just after a measurement, the time we discharge our sensor again to make sure that it's really at least close to 0 volts. Then my resistor value in mega ohms, we need that for the math, that's 5.1. And then on average and measurements, which is currently 10, that was enough. Remember, when we were measuring frequency, we were measuring about 500 milliseconds oscillation in the kilohertz range. So even when single cycles varied a little bit in the period, that totally averaged out. We don't have that luxury now. We have to average over several measurements to get rid of noise. Still, commented out here my conversion factors to milliliter. We will do that when we're sure it's actually working. Now, in the setup, nothing changed. Initializing my serial. My drive pin is an output, and I set that drive pin to low, so it's a defined state, and our sensor is discharging. And now first let's get the math out of the way. I've encapsulated all the math in one float function, capacitance in picofarads, so 10 to the power of minus 12 farads, and it gets our resistance in mega ohms, so R, our charging voltage, or VB for battery, formulas, in volts, then our charge time T in microseconds, and then the voltage across our capacitor at the time T in volts. Remember, the formula was our charging time T over our resistance R over minus the logarithm of 1 minus the voltage across our capacitor at the time t over our charging voltage. And now, yeah, you can read that for yourself down here. That's exactly that formula. Note, we have here mega ohms, that's 10 to the power of 6. And we are dividing our time, which is in microseconds already, so 10 to the power of minus 6 by that. That gives us in the end something, a factor of 10 to the power of minus 12, and that's picos. So the result here, if I put that into code without additional factor, is in picofarads. Now for the measurement itself, which is done here by that float function measure capacitance in picofarads. I have two variables here unsigned in, ADC value discharged and ADC value charged. This is just the results of analog reads. First, I drive my drive pin low to discharge and I wait for the discharge time to have passed. And then I do an analog read on my sense pin. This gives me, of course, my ADC value discharged. I do that because you not necessarily get really down to zero. There's still some noise and inaccuracies in the ADC process, so you might get 5, 6, 9, whatever. So, and here's my first sanity check. So if ADC value discharged is greater than 10% of our full scale, then I print out an error, because then my discharge time was not long enough and I don't want to use that measurement and I want to correct my constants. Okay, now we are discharged. Now I do a digital write on our write pin to a high level, that is we start charging. Then I do a delay in microseconds for my charge time, and then I take another analog read on the sense pin, which I store in the ADC value charged after that charge time. And after I did the ADC stuff here, I do a digital write drive pin low, because usually we want our sensor to be discharged, okay? Please note, don't do that before you do an analog read. It states explicitly in the ATmega 4809 datasheet that you should avoid switching pins, output pins, high, low, directly before you do an analog read, that is, use the ADCs. That might create additional noise and stuff. Then I have two more sanity checks here. First, if my ADC value charged is greater than 90% of the full scale, I print out an error, because I'm too far at the 5 volt mark. Maybe I'm at the 5 volt mark for a time and don't know it. So I want to be at least 10% below full scale. And my second sanity check is if my value charged is below 20% of full scale, then I also print out an error. So during my voltage measurement, I want to be in a band between 20 and 90% of full scale, just for accuracy reasons. Again, if that doesn't work out, change the constants. And to help me with that, I have here a little insert in the code, which is currently not included because I didn't define debug here, where I just printed out my ADC values discharged and my ADC values charged while I was tuning the constants. I gave you already a hint what starting values you could use. Anyway, and then I simply return, yeah, that was our math, our capacitance in picofarads, delivering here our resistor value in mega ohm, that was a constant, and then I convert here my ADC value discharged into the charge voltage. That's 5 volt here, and that was really the voltage at which we started charging. Yeah, just to eliminate that error. And then I give the charge time against a constant into our function, and then I actually give here the difference in volts between our charged and discharged voltage across our capacitor as the voltage across the capacitor. That's it. Since we encapsulated everything in functions, not much is happening in the loop. I have here a float capacitance picofarad and an unsigned measurement. Capacitance picofarad is initialized to 0. Then I go through a loop for my average n measurements, and I repeat just the measurement capacitance in picofarads and add that up into my capacitance picofarad variable, and at the end I divide my capacitance in picofarads by the number of measurements I did. Yeah, just a little averaging here to get rid of the noise. And then I simply do a serial print of my capacitance here, and hopefully, if we are measuring accurate enough, we can later on convert that back into milliliters and print that out too. Anyway, print ln and delay 1 just to make sure. I don't know who made that suggestion. Somebody made the suggestion to make sure that the serial buffer is really empty before doing any measurements. That would help too. Thank you for that. And now let's have a look at the serial monitor. As you can, that side probably. So as you can see, we are dry and we are measuring 53 picofarads? That's eerie. Because, I don't know if you remember, but we measured that thing at one point dry, that's probably mirrored, but dry, at 50 picofarads with my multimeter. And the 5 in the 50 was the least significant digit on my multimeter in that measurement. So we're basically spot on with the capacitance measurement. Okay. So dry, 50 picofarads. You know the game. And yes, I enhanced here with some Lego Technic the attachment of my sensor. So let's do this. 100 milliliters, let's say 85.5. 200 milliliters, 64.5 again. It's a little bit fluctuating. 300 milliliters, yeah, spot on. 74. Let's call that 74. Let's call that 74. 400 milliliters. 84. 500 milliliters. Spot on. 90. Oh, let's look at the time. Let's say 90. It's fluctuating a bit. 93. Let's say 93. And 600 milliliters, 104 picofarads. And that again is quite eerie because Back then we measured that with 110 picofarads, and the second one being the least significant digit on my multimeter. So again, we're actually measuring capacity. Now let me put these numbers in my Excel again. And here's the chart. So red is our measured capacity, and the black line is the linear line through all our data points with the least squared error. And this looks really good compared to our software oscillator attempts from the last video, which were all a little bit, atrocious. What's even more interesting, if we compare that to our hardware oscillator attempt, you notice something? We are a little bit over our linear curve here at the beginning, and then we are a little bit under, and then we are going back a little bit over. And by the way, the error is approximately the same. These curves are very similar. So we are now actually measuring, obviously, errors in our geometry of our sensor. These are not measurement errors, but errors in our sensor itself. I mean, you couldn't ask for more, could you? And here are our raw numbers in the Excel sheet. I went over the details of that Excel sheet in the part where we talked about the hardware oscillator. If I haven't carded it yet, card here, link in the description. Anyways, our factors B and A that we can use to convert our period, that is now obviously our capacitance, into a level. 11.5, 3 digits should be enough, and 569, 3 digits should be enough. Let's put that into our code. Okay, I added our two conversion factors variables here. So our constant float conversion factor, so rounded to 3 digits, 11.5. Yeah, that's correct. And our conversion offset, which is minus 569.0. Only 3 digits. That's accurate enough. Okay. And I also uncommented here the serial print now for our milliliters, which is simply the capacitance in picofarad times our conversion factor plus our conversion offset. Now let's do the reverse and fill up our container according to what our little microcontroller tells us to. So we are off to a little error when everything is dry. We saw that in the linear line of 44 milliliters, but let's fill that up until we had 100. Okay, close enough. Where are we? Oh, a little bit below 100, but it also says a little bit below 100. We're making wave inside our container. Okay, but that is now spot on, and yeah, we are a little bit below, but that's okay. Let's go until we hit the 200. Yeah, close enough. And we overshot that, but by 1 marker. But still, that's quite okay. Let's say 300. Okay, close enough. And our error reduces, of course, but yeah, quite close. And 400. Okay, close enough. And our error is, okay, at 400 we have no error. But if we have a look at our curve, we see that, yeah, at 400 the error, that's a 400 point, is basically 0. But again, this is geometry, yeah, when I cut that from hand, the copper pads, of our sensor, not our measurement. And 500. And you see these spikes in capacity, but that's really just waves going up and down. Yeah, close enough, and we're almost, yeah, that's good, 500. Now for the 600, and I expect a little error there again. And yeah, perfect, perfect. Well, not perfect, but within our setup, that is really reasonable. And we're just using, you know, our microcontroller plus one single resistor. Now, I would very much like to say that's it for capacitive liquid level sensing. However, as you can see, I filled now up my container with very dirty water from the sink. So some detergent in there and hopefully nothing organic or not much organic. Anyway, we are at 600 milliliters and we are now measuring, easily 650 milliliters and a capacity of, let's say, 106 picofarads, easily. And if you remember, at 600 milliliters with clean water, we measured 104 picofarads. So our measurement is now of, two markers, 50 milliliters. We're thinking there's 50 milliliter more in here. And remember, our measurements were not perfect, but the largest error we had was at 200 milliliters, where we thought it was 225 milliliters. So, yeah, that's an error. And if we have to go back to part 1 to explain that. And in part 1, if I didn't run out of cards, card here, a link in the description, we learned that the capacitance is, amongst other things, proportional to our, where was it? Relative permittivity or dielectric constant of our, isolating medium or semi-isolating medium between our capacitor plates, our two charged whatever things. And the values are quite different. For example, between water, that's about 80, it's more like 78 and not percent. That has no dimension, 78. And salt water, I gave you the number back there of 32, but that is for saturated salt water. And seawater has approximately 69, so already a little bit lower. And this toxic stuff here I got out of the sink. This has obviously a higher dielectric constant, and so our measurement is thrown off if our container, which we want to measure the fill level in, is filled with different liquids. But there's an approach to alleviate that problem. But we will talk about that in the next video. Before I bid you farewell for today, I wanted to talk about the little issue of me changing up that resistor here from 10 mega ohms to 5.1 mega ohms. Here's my old 10 mega ohm resistor. You can hear the details are not really important. You can see here on the scope one of our charge-discharge events. And please note that, extreme noise here when we are in the discharged state, so near 0 volts. And if I change the time scale a little to 20 milliseconds, remember 20 milliseconds per division, that would be 50 hertz. And we also talked about that. I can't remember in which part. These sensors are kind like a great antennas. I can improve that antenna even more when I touch the sensor. And then you see, that's that's 50 hertz. That's messing up absolutely everything. And the higher our resistor value is, the higher is the input impedance here from our antenna. At 50 hertz we can forget about our 50 pico or 100 picofarad capacitance here between the input of our Arduino and the ground, and where I'm now measuring with our oscilloscope. So with a 5 mega ohm resistor, you can halve the noise here compared to a 10 mega ohm resistor. And that was the only reason that I used that 5.1 mega ohm resistor. Depending where you're located, it might be 60 hertz, of course. That's it for today. As you can maybe hear, my chopper is waiting for me. No, that's a hospital on the other side of the hill. Anyways, next time, and I don't know if it will be really the next video, but at some point we will handle that problem. I just have to redesign here my broomstick sensor in a certain way, so I can show you how to actually correct for the error for changing liquids.  'Liquids. 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 'Liquids.